All right, so today we have this integral we want to evaluate or find the antiderivative of this function, integral e to the 2 cosine x times sine of x dx. All right, so today we're going to be looking at the chain rule. And I kind of like the u substitution. Excuse me, we're doing a u substitution today. And I like to think of it as like the reverse of the chain rule. So for those that recall or don't recall, the chain rule said something along these lines, that if you took the derivative, put this down here, of a composition of functions, it was equal to the derivative of the outside function, f, composed with the inside times the derivative of the inside. That's what the chain rule said. So what we're doing here essentially is we're going in reverse, okay? And the way u substitution works is that you're looking for a integrand, which is the integrand is just the inside of the integral. It's like in this case it would be all this stuff right here, for such that it's a composition and of functions, and the derivative of like the inside appears there, okay? And that inside, or the function whose derivative appears, is what we call u. That's why it's called a u substitution. So for example, where I have the integral right here, I would call u g of x, and then du is the derivative g prime of x dx. Du and dx are called differentials, okay? I'm not really going to go into that today, but the reason we write it this way, obviously, well, can't you write it as like du over dx, which is really what you're doing here. You could, but it's for like bookkeeping and note-taking purposes that we write a notation. It's just a little simpler. Well, when you do those two substitutions, the u and the du, and rewrite the integral, what happens is that integral now becomes what I have circled here in orange. And the idea here is, with this u substitution, is that it boils everything down just to finding the antiderivative of the outside function f, okay? Now, with a u substitution, I think of it, this is like a mix between an art and a science for solving these problems, for picking the correct u. So it's not always straightforward in the sense that when you're looking for a u, in the sense that you just don't always know immediately what you should pick, okay? Sometimes it's going to be a little difficult, and I have these tips here. So first tip is u is typically something whose derivative appears in the integrand, okay? So something that, for example, if I had x to the third plus 7 to the 8th power, then I would have x squared. Notice how the derivative of x cubed plus 7 would be 3x squared. So that's what this kind of looks like. So what I'm getting at is I'd pick u to be the x cubed plus 7. That's what I mean by that. Next question here, next tip is try to find something similar to the integrand that you know the antiderivative of. Okay, so if I look at this for a second, I might say to myself, that kind of looks like the integral of like 1 over 1 plus x squared, which is tangent inverse, sort of looks like that. And what I'm trying to get at is I would try to make appropriate u for me to turn this to look something like what I have here, okay? And then the last but not least, try to use algebra for u substitution if you can. So this is like, for example, if I had an integral of this sorts here, yeah, I would definitely try to use algebra before even picking a u sub. I would think of u sub as like the second thing I would try. I would try to use any algebra or trigonometry for that matter before I try a u sub, just because you want to usually go with the easier route whenever you're working with an integral. So I would pick that. Well, anyways, let me go ahead and go back to the original problem, which was the integral of e to the 2 cosine x times sine of x. So I'm going to pick my u here, my next step. And in our case, my u would be what? Well, I would say 2 cosine x. And the reason for that is because the derivative of 2 cosine x is minus 2 sine x dx, which appears right here. Okay, so that's an indication that would be a good pick for you. And the other thing that I like is u, 2 cosine x, is part of a composition. It's composing e to the x and 2 cosine of x. It's on the inside, think of it of e. Okay, so once we do that, we're gonna rewrite our integral now in terms of our variable here. So when we rewrite it, we would have e to the u, and then the sine x dx part. Well, I have du as minus 2 sine x dx. It's not exactly sine of x, but what I can do is this. I can go ahead and multiply both sides of the du by negative 1/2, and sine of x dx would be minus 1/2 du. And yeah, that whole thing with the sine x dx will get replaced by that. And that's what you often have to do with these problems. You pick your u, you find your du, and your du is often a multiple of your integrand that appears for which you took the derivatives being taken. So, right, so that sine x dx part, that's negative 1/2 of the negative 2 sine x is what I'm saying with that. So anyways, you know you've reached success when you've, and this is more like an ad hoc method, when you've got to an integral that has only the new variable u, and then you can integrate somewhat easily. So yeah, I can integrate e to the u. The antiderivative of e to the u is just e to the u. Let's see, and that's the other point, is you want, no pun intended, a integral that you can compute easily at the end of the day. Okay, and I sometimes people, it's like you're turning something that's more complicated to something easier. You're doing a little bit of mathematical magic here. And I'm going to put my u back in. That's the last part. You start with x's and you end with x's, and there you go. And you could always check your work, by the way. If you took the derivative of this, you should all get what we had originally up here. Okay, so that's how you check your work, because this is an antiderivative, which is what function, when you take its derivative, gives you what you have in there in that circle. Sorry, that not including the dx there, I apologize. All right, well, I hope this helped. Thank you for your time.